Welcome to today's paper reading. Today's paper is titled, SPVLoc, Semantic Panoramic Viewport Matching for 6D Camera Localization in Unseen Environments. This paper was published on AR14 by Niklas, Gard and colleagues from Fraunhofer Heinrich Hertz Institute. This paper introduces SPVLoc, a method for global indoor localization that accurately determines the six-dimensional camera pose of a query image with minimal scene-specific prior knowledge. The approach uses a novel matching procedure to localize the camera's viewport within panoramic semantic layouts of the indoor environment. These panoramas are rendered from an untextured 3D reference model, which includes approximate structural information about room shapes and door/window annotations. The paper demonstrates that a straightforward convolutional network can effectively match images to panoramas and ultimately to the 3D model. The method ranks panoramas based on a viewport classification score and estimates the 6D relative pose between the best matched panorama and the query image. Experimental results show that SPVLoc efficiently bridges the domain gap, generalizes well to unseen scenes, and achieves superior localization accuracy compared to state-of-the-art methods. Indoor camera localization is a fundamental challenge in computer vision, aiming to precisely determine a camera's position and orientation within an indoor environment. This task has various applications, including navigation, augmented reality, and building management. Current methods often rely on extensive scene-specific data, which can be costly and time-consuming to acquire, limiting their applicability in many scenarios. Figure 1 illustrates the SPVLoc method for 6D indoor localization. The method determines the 6D camera pose by identifying the image's position and orientation relative to synthetic panoramas. The best match among the panoramas is selected through semantic viewport matching, which ensures accurate localization even in unseen environments. In the field of indoor camera localization, several methods have been developed. Some rely on 3D models generated through structure from motion from registered camera images. Others use neural networks to perform regression for absolute pose estimation. Additionally, synthetic renderings from building information models (BIM) have been utilized to achieve real-time localization without real-world reference data. For relative pose regression, frameworks often enhance generalizability through image comparisons. Retrieval-based methods like NetVLAD and DenseVLAD identify similar images in a database to provide a starting point for pose estimation. Graph neural networks, GNN, have also been employed to refine camera pose estimates. Regarding perspective to panorama matching, this aspect has received limited attention. However, distortion-aware convolutional filters and sliding window approaches in feature space have shown promise in improving matching accuracy. Figure 2 provides an overview of the network architecture designed for 6D localization. The architecture is divided into two main branches, the query branch and the panorama branch. The query branch processes the input image, while the panorama branch handles the panoramic reference images. The key feature of this architecture is the depth-wise correlation, which allows information from the query branch to be fed into the panorama branch, facilitating the integration of features from both domains. The network includes 3 task heads dedicated to predicting the corresponding viewport within the panorama. Additionally, there is a separate task head that predicts the relative pose offset, which is crucial for accurate localization. This design enables the network to effectively match perspective query images with panoramic references, thereby enhancing the precision of 6D pose estimation. SPVLoc is a method designed for 6D indoor localization of a 2D RGB query image within a semantic textureless 3D scene model. The model follows the structured 3D annotation format, which includes elements like walls, doors, windows, ceiling, and floor. The process involves several key components: viewport matching, pose regression, and optimization and inference. One of the main challenges in this process is dealing with perspective distortion and the domain gap between photographic RGB images and rendered semantic panoramas. Additionally, handling occlusions is crucial for accurate localization. Figure 3 illustrates the architecture of the pose head, which is crucial for estimating the relative pose offset of the camera concerning a panorama rendering. The pose head employs 3 convolution blocks, with the first two followed by a max pooling layer to compress the features. These features are then flattened into an 1D embedding. Our star operator is an element of RC, where C equals 640 for a panorama of dimensions 256 by 128. An optional feature of the pose head is its ability to handle different camera field of views during training and testing by normalizing our star operator and multiplying it by the horizontal field of view angle in radians. This normalized result is fed into a 4-layer MLP, which produces the 3D offset to the query image location. TI is an element of R3 and a rotation given as the logarithm of the unit quaternion re equals log Q. IJ is an element of R3. The MLP is evaluated using two loss functions. LP1 assesses the precision of the relative translation, and LP2 evaluates the accuracy of the final rotation estimation, both computed using the L1 distance. In this section, we discuss the datasets used for our experiments, which include structured 3D and Zillow Indoor. Both datasets are transformed into the S3D format to ensure consistency. Our test sets consist of perspective images with varying field of view angles and camera orientations. We evaluate our method using several metrics, including the fraction of correctly localized frames, median errors in rotation and translation, and recall metrics for the top 1 and top 3 best matches. Figure 4 illustrates the process of preparing data from the Zillow Indoor (Z&D) dataset. On the left, annotations are used to generate 3D reference models. On the right, resampled panoramas are shown to create perspective images for both training and testing purposes. These perspective images are registered in the 3D model, ensuring that the semantics for each image are known. This setup is crucial for tasks such as 6D pose estimation and structured evaluation, where the accuracy of the semantic information is paramount. Figure 5 presents qualitative localization results for SPVLoc. The top row displays the query camera images, followed by renderings from the semantic 3D model with the top 1 estimated poses in the second row. Green boxed images indicate successful localization for the top 1 match, while yellow boxed images show accurate localization for the top 2 match. The red box signifies a failure case where localization was not achieved. The third row shows the reference panorama, the selected viewport bounding box corresponding to the camera image, and a semi-transparent overlay representing the estimated viewport mask. These visualizations help in understanding the performance and limitations of the SPVLoc method in various scenarios. Figure 6 illustrates the reference positions for different grid sizes used in the study. The global grids are shown with sizes of 0.7 meters and 1.5 meters, while the local grid is depicted with a size of 1.5 meters. The grids are positioned from left to right, providing a visual representation of how these grids are applied in the context of the experiment. This figure helps to understand the spatial arrangement and the impact of grid size on the performance and efficiency of the model. Table 1 presents a detailed comparison of our method with the state-of-the-art baseline on the Z&D and S3D datasets. The table highlights the median translation error, TERC, in centimeters and the median rotation error, radial, in degrees for instances localized within 1 meter. Additionally, it reports recall metrics at various translation accuracy levels, including recall for instances localized within 1 meter and 30 degrees, and top 3 recall at 1 meter. The hours model refers to our method tested with a slightly different test set, incorporating pitch and roll rotation variations, plus or minus 10 degrees. The comparison underscores the superior performance of our method in terms of localization accuracy and recall metrics, particularly in scenarios with variable field of view and angle variations. Table 2 presents an ablation study of SPVLoc variations on the Z&D dataset with a 90-degree field of view FOV. Unlike Table 1, which focuses on 2D metrics, Table 2 introduces TER, representing 3D position errors, and RARE, denoting 3D rotation errors. The study evaluates the impact of removing specific components from the SPVLoc network, such as perspective supervision, query December, and the view segment task head, view December, which both lead to reduced network performance. Additionally, the exclusion of negative samples from different rooms, neg, samples, significantly decreases the accuracy of localized images. The table also highlights the performance drop when replacing the image encoder EfficientNet-S with a smaller ResNet-18, increment ResNet-18. Overall, the ablation study provides insights into the critical components of SPVLoc that contribute to its localization accuracy. Table 3 highlights the impact of different grid sizes on the accuracy of localization in terms of 10 cm and 1 m recall deviations from a baseline configuration. The data reveals that while increasing grid size can significantly reduce the number of samples per square meter, it also affects the localization accuracy. Notably, refinement processes are shown to notably enhance the 10 cm recall across various grid configurations. For the largest local grid configuration with refinement, the 1 m recall only experiences a minor decrease of 1.18% compared to the baseline. This suggests a trade-off between the density of scene sampling and the necessity of refinement, yet the method consistently achieves robust results even with very sparse sampling, making it particularly effective for large-scale scenes. Table 4 highlights the performance differences between a fixed field of view (FOV) network and a network designed to handle varying FOV. The fixed FOV network performs optimally at a specific angle, but demonstrates a loss in precision when tested with images of different FOV. Conversely, the proposed network, which is designed to be FOV independent, maintains stability across varying FOV conditions. This enhanced flexibility of the proposed network, despite a minor performance degradation, is argued to be justified in practical, real-world scenarios where FOV can vary. Table 5 illustrates the effect of increasing angle variation in test data on the network's performance. As the range of roll and pitch angles in the test images increases from plus or minus 0 degrees to plus or minus 20 degrees, there is only a slight increase in median errors for both rotation and translation. Specifically, the median translation error rises from 14.46 cm to 15.91 cm. And the median rotation error increases from 2.35 degrees to 2.60 degrees. Despite these increases, the network maintains its ability to handle a wide range of camera angles, demonstrating robustness in real-world scenarios where camera angles can vary significantly. Table 6 presents the timing performance of our method on the Z&D dataset using a NVIDIA Tesla V100 GPU. The table compares our method against PFNet 19, and Laser 30, highlighting the significant reduction in query time. Specifically, our method achieves a query time of 1.66 plus or minus 1.06 milliseconds, which is notably lower than the 8.31 plus or minus 0.64 milliseconds of Laser and the 28.63 plus or minus 11.54 milliseconds of PFNet. This performance places our approach closer to real-time for moderately sized scenes. The table also breaks down the query module time into components such as EfficientNet V2S, correlation, and pose, providing a detailed view of the method's efficiency. This paper presents a novel method for scene-independent 6D localization in indoor scenes. The method involves a new approach to multimodal image matching, which is both efficient and scalable. It significantly outperforms existing state-of-the-art methods in terms of localization accuracy and inference speed. The inclusion of a 3D model helps to reduce ambiguities, allowing for precise estimation of 6D poses. Looking ahead, the authors plan to combine localization with image analysis to enhance digital building models and explore potential applications in augmented reality scenarios. Thank you for watching.